Hello world, my name is Dino Anastasopoulos and today I will be presenting my research, investigating the applicability of generative adversarial networks on non-natural image types. I'd like to start by thanking my supervisor, Dr. Richard Klein, for his assistance throughout this project. It would not have been possible without him. So what exactly is this, and why are we doing it? Most computer vision and generative modeling has been in the domain of natural images such as human and animal faces, but the world is changing rapidly with Web 3.0, the metaverse, and related technologies like virtual reality. For this reason, we need to build better models for digital, computer-generated, and discrete types of images, such as cartoons. This project aimed to investigate how plausible it would be to use GANs to automatically create cartoon characters. This kind of tool could be used to create background characters for crowds in video games and cartoons. It would also help artists overcome creative block by giving them new ideas for characters. Now, what are natural and discrete images? On the left, we have a cartoon character in which all pixels in a bounded region take on the exact same color. For example, the pants are a uniform gray color. This is due to the fact that cartoons are unaffected by lighting, reflections, and dispersions. These graphs show the pixel intensity values for the red, green, and blue color channels, with a value of 0 being black and a value of 255 being white. We can see that the graph for the cartoon is discrete, with spikes at specific intensity values, yet no pixels taking on the other values. On the right, we have an example of a human face which was actually generated by a GAN. Neighboring pixels in this image will all have slightly different intensity values due to lighting and shading in the real world. This can be seen in the graph, which is a continuous distribution over the entire domain. A generative adversarial network is a type of generative model which consists of two neural networks competing against one another in a cop versus counterfeiter style game. The generator network is the counterfeiter and aims to trick the discriminator by creating images that look exactly like the real images from the dataset. It takes in a vector of random noise, forward propagated through the network, and outputs an image. Pretty magical, right? On the other hand, we have the discriminator network, the COP. This network aims to catch out the generator by determining which images are from the real dataset and which ones have been generated by the counterfeiter. So, what did we do? The only existing discrete image dataset is the cartoon set by Google. The issue with this dataset is that the cartoons are simply interpretations of people's faces and is therefore uninventive. A new dataset was curated using a web scraper built with PyAutoGUI on the Go Wreck Yourself Rick and Morty style character generator system. This dataset consists of only 10,000 images, but there are more than 10 to the power of 20 possible unique combinations of all the available features. This dataset is creative, diverse, and the first of its kind. The first model trained was the deep convolutional GAN. The generator receives a random noise vector and uses fractionally strided convolutions to increase the spatial resolution until the desired image resolution is achieved. These fractionally strided convolutions can be replaced with bilinear or bicubic upsampling, followed by same convolutions. The network uses ReLU activation functions with a tan-H activation on the output. The discriminator receives an image and uses strided convolutions to decrease the spatial resolution to achieve the desired scalar output. Leaky ReLU activations are used with a sigmoid activation on the output. Both networks make use of batch normalization. The second model implemented was StyleGAN2 ADA. StyleGAN consists of a style-based generator with a network which maps the random noise input to an intermediate latent space vector. The use of adaptive discriminator augmentation helps to avoid overfitting and decreases the need for large amounts of data, with only 10,000 images still giving good results. So, did this work? The quality of generated images can be analyzed simply by looking at them, but we also have the Fréchet inception distance to give us a good quantitative metric. The FID score is closely related to human perception of image quality and works by measuring the distance between the distributions of the real and generated images, with the lowest score being better. The current state of the art was achieved by StyleGAN on a dataset of human faces at a remarkable FID of 2.42. Our StyleGAN model achieved an FID score of 28. Our DC-GAN model at a resolution of 64 by 64 achieved an FID of 170, and an FID of 263 at a resolution of 256 by 256. At a low resolution, the DC-GAN model quite accurately learned most of the real features from the dataset and can generate a wide variety of unique characters. However, at a higher resolution, the model learned the basic structure of the characters, but the quality is low and individual features are barely discernible. It also suffered from mode collapse, meaning that it's only capable of generating a small subset of samples and features from the dataset. The StyleGAN model achieved near-realistic results. It learned to generate every unique feature in the dataset, but cannot accurately generate the finer features like the eyes. The model is also capable of accurately reproducing an image from the real dataset. So where do we go from here? Using GANs for this application is an over-engineered solution, since the character generator already has trillions of possible unique combinations. Perhaps we could use a more systematic approach to create the actual features like heads and legs and build up the character piece by piece. We discovered that models built for natural images have a few weaknesses when used on non-natural images. We need to build more datasets in this domain with models specifically for these. Transfer learning could help combat the need for large amounts of data, but we would first need a solid baseline within the domain to transfer from. I'd like to end with a video of a walk through the latent space of the StyleGAN model, while reading a quote worth pondering. The worry is not about the increase in artificial intelligence, but the decrease in human intelligence. I hope you enjoyed my presentation and learned something interesting. Thank you for coming.